In this question from the chapter 5, we have to prove that this function fx is equal to mod x minus 1, where x belongs to R, is not differentiable at x is equal to 1. In fact, any modulus function is not differentiable at its turning point. Let's say, for example, if I explain using graph, you see that if I write a modulus x, then this function, the graph of this function is something like this, where this function is, we cannot draw a unique tangent at x is equal to 1, right? And that's why we say that the function is not differentiable at x is equal to 1. Similarly, if I write, let's say x, which is in this question, it is mod x minus 1, comparing x minus 1 with 0, we get x is equal to 1. So with that, say that this function is not differentiable at x is equal to 1, as we cannot draw a unique tangent at this point. There's infinite tangent. We can do more examples. Let's say, for example, if I write modulus x plus 1, or say x plus 2 in this case, so x is equal to minus 2, that means it is not differentiable at this point, that is minus 2, but otherwise it is differentiable throughout. Moreover, you should also know that modulus function is continuous throughout. That is x is equal to R, it is continuous. But then we do not have to show here using graph. We have to use this concept that LHT should not be equal to RHT is what we have to prove at x is equal to 1, has to be at x is equal to 1. Now for that, we are going to use a formula that is f dash a is equal for, f dash a is equal to limit h tends to 0, f a minus h for LHT minus f of a over minus h. Now before that, I'm going to break this function. The function here is x minus 1, clearly for x greater than 1, it's going to be x minus 1 only. And for x less than 1, it should be minus of this, right? It should be minus of this, which is 1 minus of x minus 1 is what? Minus x plus 1. We can write 1 minus x instead. Right. So we have split the function. And now I'm going to use this LHT. So for limit h tends to 0, what I'm going to calculate is f dash 1. That is f dash 1 limit h tends to 0. F a will be replaced with 1. So 1 minus h o minus f of 1 over minus h. Now this is limit h tends to 0. F1 minus h, and we are doing left-hand derivative. So clearly left-hand derivative is this. So we are going to replace this x with 1 minus h. So it's going to be what? 1 minus x being replaced with 1 minus h. And this is f1. So what is f1? So fx is equal to mod x minus 1. That means f1 will be 0. That is 1 minus 1 is equal to 0. So f1 is 0. That divided by minus h. So finally, it's 1 minus 1 plus h over over minus h. This get cancelled, which is equal to minus 1. So we are getting LHT as minus 1. Now let's do the RHT. For RHT, the formula will be f dash a is equal to limit h tends to 0. This would be f a plus h, right, for RHT, minus f of a over positive h. Now we are calculating f dash 1. So it should be limit h tends to 0, f a plus h, that means f1 plus h minus f of 1 over positive h. So this is limit h tends to 0, 1 plus h, 1 plus h, that means right-hand derivative. I'm going to replace this x with 1 plus h. So it's going to be replacing this x with 1 plus h. So it's going to be 1 plus h and this minus 1, minus 1. And f of 1 we calculated at 0. Placing x is equal to 1 over here, we got 0. So I'm writing 0 over h. So here minus 1 plus 1 get cancelled. And what did we get? We get h over h, which is equal to 1. So clearly we can see that here RHD and LHD are not equal. LHD is not equal to RHD at x is equal to 1, right? Right. Not everywhere. At x is equal to 1, LHD is not equal to RHD. Hence, it is not differentiable. So an important conclusion that you should get that a modulus function is not differentiable at its turning point. Otherwise, it is differentiable everywhere. So had the question been x minus 3, then would have said that it is differentiable everywhere except for x is equal to 3. Similarly, if the question were fx is equal to say x plus a, so we'll say that it is differentiable everywhere except for x is equal to a.